So I want to talk about, so far in the semester, when we've been dealing with rigid bodies, I've been always telling you where the center of mass or center of gravity of an object is. Right? What we're going to do now is that we want to look into how can we calculate the center of gravity and center of mass, centroid, which basically includes center of area, center of volume, center of a line. Right? Where does it lie? On a line, on an area, on a volume, on a mass, where the center of gravity or center of mass is. All right. So that's going to be the topic. And once we learn about centroids, actually we can use centroids to study distributed loads. Right? We'll talk about it. But so far, all the forces and loads I've shown you or you've seen in this course, whatever we've covered, are point loads, meaning that there's only one load applied to a point, to a place, right? I usually put one arrow as the load. Now, in reality, a lot of forces, you not barely, but you mostly see forces as distributed loads, right? Loads that are when you have two surfaces in contact, right? If you think about this the normal force here that we had, NA, that normal force is actually a distributed force, right? Something like this. Like there is a force, constant force applied to the whole surface. So when we put N there as the normal force on a specific spot, that's why this X is unknown in a lot of cases, because we don't know the distribution of this load. We don't know if this distributed load is distributed that way uniformly, or is distributed this way, where one side there's more load on that than the other side. If you remember the box example, right? When I was talking about the box sitting on the floor, right? I said it depends on where you apply the force. If you apply the force all the way at the top, your N is going to be closer to this end. If you apply the force that you applying to push the box somewhere closer to this lower part, your N is going to be more closer to this end. Why does that happen? Because the way the load is distributed changes. We'll talk about it when we get there. But we find the equivalent point load for distributed loads, and that's how we work with distributed loads. But it's further from now, a couple of classes from now. Just you know that that's another application of centroids. When we study centroids and we want to find the center of an area, typically, or even a volume in two-dimensional space, we use that center of area is also important because we can find the point load equivalent of a distributed load. Right? We'll talk about distributed loads and how can we use centroid to calculate that. So I just wanted to point out what is the application of this, specifically centroid, finding centroid. Center of gravity is obvious. You need to find the center of gravity to be able to put the weight load on center of gravity, right? So let's put it under center of gravity, center of mass. I think that's the title from your textbook, and centroid. Pretty much all of these we're going to cover. Now we start with center of gravity, and you will see from there how can we extrapolate and understand or calculate the other quantities. All right. So let's start with center of gravity. Center of gravity. Now, think about a rigid body as something, right? A rigid body is basically nothing but a body composed of infinite number of particles, right? If you go very like microscopic level, any rigid body, a pen, a cup, anything, is basically composed of infinite number of small particles, right? And each of these particles have some weight. Depends on how small they're going to split it, right? Well, they're going to be The smaller you split this rigid body into, the more you split this rigid body, right, you're going to get the smaller particles, but each particle has its own weight. Let me write it here. A body is composed of infinite number of particles. All right. And we'll say, well, obviously each of these particles have a weight. I have a weight. Wait. Let me bring the figure I have here. That is something that's going to help me move forward. Let me make it actually bigger. This is something we need. Each particle have a weight of delta W. Let's just follow it. No, so n number of particles. In this case, you see particle 1, particle 2, and particle n. I've subdivided this. You see that there are more particles, there are more boxes here. Let's say each a particle forming this rigid body, some shape. It's a rigid body. Now, let's write if there is a. All right, let's write it this way. Let's say we have a center of gravity somewhere, right? The center of gravity of this body is somewhere here. And it's r away from the origin. Right? It's called RCG, position of center of gravity in this coordinate frame. All right. Now, what I want to do is that I want to write summation of moments of all the forces about point O. Right? This is a rigid body, a bunch of forces. Remember, if you find the moment at point O, well, each force is creating some moment about point O, which basically is the distance multiplied by the value of, or the magnitude of the load. That, and remember, we are finding the equivalent of this system. What I'm trying to find is that what this is, I want to say, well, I want to find the spot, center of gravity, that I can put the weight on it, weight of the whole structure, W, which is basically delta W1 plus delta W2 plus weight of the all these particles. Right? In this coordinate frame, if I be more accurate, I try to put the coordinate from there as close as it is to what we have up there. Z, and this is X, and this is Y. This is my R CG. So I want to go from this rigid body to what I have at the bottom. That's what we were doing so far. We've been doing so far, right? We've been I've been telling you where the center of gravity is, and you were putting a mass on the center of gravity. Right? So as a result, whatever I get, the summation of moments about point O for the top one, right? This is a vector, should be equal to the system at the bottom, which basically the moment for that is RCG cross W. Right? These two systems are the same. So whatever is the moment of all these small forces for each particle, the weight of each particle about point O should be equal to the moment of the total weight when it's put on the center of gravity. All right. That's the logic that we're following here. So if you actually follow this logic and write this in a vector form, here's what you will get. If for W1, I'm going to decompose it here. I might be able to use a better color or might not. So this is on X, this is on Y. So this is going to be X bar, let's call this X1, and let's call this distance, and let's call this distance Y1. For W2, let's call this distance, oh, that was W2, my bad. So this should be X2 and Y2. Should be X2, should be Y2. This should be Y1, and this is X1. For that one, when we are dealing with Wn, if you look at it, this is its, this is from here to here, it's Xn. From here to here is Yn. What I'm saying is that there's just coordinates of each point, X and Y, of each point where the particle is in this coordinate frame. And remember, we are just in XY plane, so no worry about the Z direction for now. All right. So if you write that moment, right, if you're in the plane, you'll get two set of equations, one in X direction, one in Y direction, right? Or better to say, summation of moments about point O in X, in Y gives you X components, and summation of moment, the X component. I just write it. If you write it, you write W1, the W1 is X1I plus Y1J, and you have R also, decompose it into vectors. Here's what you can write. This becomes X bar, and X bar and Y bar are where the center of gravity is. This is X bar, this is Y bar. All right, so this becomes X bar W, and this becomes equal to Y bar W. If I expand these two, here is what you get. These all are coming from this first equation. This, if you write everything in vector form, knowing where your center of gravity is and each particle is, we actually get to this point. Right? So from the first one, you will get X1 delta W1 plus X2 delta W2 plus Xn delta Wn. You'll get is equal to X bar delta W. Sorry, X bar W, the equivalent system. From the second one, you'll get Y1 delta W1 plus Y2 delta W2 plus Yn delta Wn. That gives you Y bar W. That means, remember, we are trying to find where where should we put the center of gravity, which means we are looking for X bar and Y bar. So if I take them out, X bar is going to be X1 delta W1 plus X2 delta W2 Xn delta Wn divided by W. Right? And Y bar would be Y1, Y1 delta W1 plus Y2 delta W2 plus Yn delta Wn. This is n divided by W. This is nothing but you can write it as a summation, right? Summation from I to n, xi delta wi over w, and this is summation of I from 1 to n, yi delta wi divided by w. Now, where am I going with this, right? Bear with me a few more minutes, you'll see where this ends. This goes going. W, you can write it as, also you can write W as summation of I from 1 to n delta wi's, right? The sum of the w's, the total weight is the sum of the weight of all the particles. I from n, I can write it better, I from n delta w, all right? So we have this fraction now, x bar is equal to summation of weight of particles, summation of the multiplication of the weight of the particle and the distance it has from y-axis, which is xr, over the sum of the weight of all the particles. Now, a little bit of math. You remember when we have now, hey, this rigid body is formed or composed of infinite number of particles, right? What does that mean? It means this n is a very, very large number, infinite. N goes to infinity. If you remember from the definition of integral, when I goes from 1 to infinity, this summation becomes an integral, right? So you can actually write it this way. You can say x bar, this color, x bar is equal to integral x dw over integral dw, and y bar would be y dw over integral dw. Right? It's just the natural conclusion when n goes to infinity, infinite number of particles, then this summation of numerator and the summation denominator, they become integral. It's a definition of integral, if you remember that. I won't go into details, hopefully you remember. Similarly, we did it for x and y, but you can see the pattern. You could get the same thing for z. Z bar would be integral z dw over integral dw. These are the coordinates of the center of gravity. Right? Remember what x bar and y bar were, what they were. They were representing where the center of gravity is in this coordinate frame. So this is what we get. These are, that's not what I wanted to do. So in two-dimensional space, x bar and y bar. In three-dimensional space, similarly, you can follow the same logic. You find z bar also. So these are coordinates of the center of gravity. How do we calculate that? We'll see. All right, I'll show you one or two examples. What we're more interested in is for composite structures that they have multiple. We know the center of gravity for each part, and we want to find what is the center of gravity of the whole structure. But this is a little bit of mathematics. I'll go over at least one example to show you how does this work. All right. So as long as you can calculate these integrals, integral x dw over integral dw, you can find x bar, and you can similarly find y bar and z bar, so you know where your center of gravity is. For any object, you can find where the center of gravity is. Okay. How about center of mass? What's center of mass? How about center of mass? We have a rigid body, something like that. You can follow the same logic, or we can use what we derived from before, right? This x bar, y bar, and z bar. Think about it this way. What is W? W, or mass, weight, is mg, right? If I take one small element here, this is gonna be dw. You can take the derivative from both sides, or can differentiate both sides. This becomes g dm. G doesn't change, so you differentiate g doesn't change, it's fixed. M changes depending on how big this element is. So from there, if you take you differentiate both sides, you'll get dW is equal to G dm, and plug that into what we had from before, right? As straightforward as that. X bar now is equal to X G dm over integral G dm. G is just a constant value, acceleration due to gravity. Just take it out and it gets canceled out. So X bar, let's show that with XG, center of gravity. Also, you know what? They're the same. So that is equal to integral dm integral x dm, dm being the mass of an element, integral dm. Similarly, you plug that into y bar, you get integral y g dm over integral g dm, cancel out g's, you'll get integral y dm over integral dm. So this becomes y bar is equal to integral y dm over integral dm, and z bar becomes integral z dm over integral dm. All right, so these are going to be your coordinates of the center of mass. As long as we can calculate these integrals, we can find the coordinates of the center of mass. So this is, I'm going to write here, coordinates of the center of mass. And that's why you see we keep throughout the course I told you center of mass, center of gravity, they're the same. They look we calculate them differently depending on what information we have, but at the end for a rigid body they are the same point. All right, because you see G is only changing factor here and it cancels out. So X bar, Y bar, and Z bar, center of gravity and center of mass are the same. They're the same location for rigid body. All right. Let's continue this. So center of mass. How about center of volume? Right? Or as they call it, centroid of a volume. If we have an object, we want to find where is the center of volume. That comes into play specifically in fluid mechanics. You'll see that a lot, that you are going to end up needing, you're going to end up, or you need to find where the center of volume is, especially when it comes to buoyancy. And you're calculating buoyancy, you need to center of volume. So how do we calculate center of volume? Right, what if we have an empty object and we want to find, it's a gallon of, I don't know, it's a container of milk. You want to find where is the center of volume. How do we calculate that? You will see it's also very close to the same idea. If I write center of volume, or we call it centroid of the volume, simply centroid. All right. Again, we use what we derived before. We know the density. All right. Think about, again, a rigid body and elements there. Rho density is equal to m over v, volume. That means m is equal to rho v. You can differentiate on both sides. Right? This element here is basically an element with dm and dv. Right? The element that has a mass of dm, some value of mass, depends on how small you make that particle. The particles that are forming a rigid body, how small you want to make it, and dv. In integral form, make it as small as possible. It goes to the number of components go to infinity. So dm Rho is a constant, is a property of a material, right? Fluid has, water has a specific density, any object has a specific density. Doesn't matter how small you make any size of an object made of that material has the same density. Right? Density doesn't change. It's not a quantity that depends on the. It's not a. Let's put it this way. It's not something that depends on the quantity. Right? So this becomes dm into rho dv. V changes though, right? When you change this part or the element as we call it, the size changes, the mass changes, the volume changes, density doesn't change. So density comes out. So we'll go back to what we derived for coordinates of the center of gravity here, and we use them again. Right? Or you can use this. This is actually better, less number of steps. We can use center of mass. Right? For center of mass for x, we know that x bar is equal to integral x dm over integral dm. Now dm is rho dv, so rho is constant, comes out. The rho integral x dv is equal to rho dv. You cancel those out, you will get x bar, the center of x components of the center of volume or centroid of a volume. You'll get x dv over integral dv. Similarly, you get the same thing for y. Y dv over integral dv. And z would be z dv over integral dv. These are going to be the coordinates of your center of volume or centroid of the volume. This is going to be the coordinates of centroid. Centroid of the volume. Or simply just center or central, center of your volume or center. All right. Now, so far, hopefully you follow. We found center of gravity. From there, we could easily find center of mass, and from there, we could easily find center of volume. Now, these are integrals. We have to calculate them mathematically. We'll see case by case. It changes. How do we actually find that dv? How do we find that dm? How do we find that dA? That's the tricky part, because these are depending on how much you remember from calculus, these are integrals in space, right? dw or dv is it's actually like this. dv, right? dx, dy, dz. It is in 3 dimensions, right? So there are ways to convert dv, this integral, into a simple one integral and then calculate that. It goes more into calculus and the way we calculate integrals for volumes and areas, right? For the area, we haven't talked about it. We'll talk about center of area next. But these are the general equations that they use to find the center of the gravity, center of mass, and center of volume.